Hello, welcome back to Physical Chemistry Energy Levels. Today I've put two videos up from a guy called Chad Orzel in America on my YouTube video list. They're really good. They're about the photoelectric effect and about Planck's law, effectively. Up till now we've just accepted quantum mechanics, but it would be good to have a little bit of background so that we know what we're doing. Because now I would like to know what happens when we heat things up and what happens when we shine light on things, to the energy levels inside them and to how they behave. If we look at the Planck video, we can see that there is a problem, there's a mathematical problem if we have a theoretical oscillator and we give it any frequency. So we have an oscillator like that, and it can have a fundamental frequency like this. So maybe it's a string, for example, and then its excited frequency is this, and then it can be excited further and further and further. And we end up with what Mr. Orzel calls the ultraviolet catastrophe, that because the wavelengths get smaller and smaller, these energy levels become closer and closer to each other, because we can have, this one is one, let's call this length, so twice that length is 1. So this wavelength is 1, this wavelength is a half, the next one is a third, the next one is a quarter, the next one is a fifth. And as they go up and up and up, whatever that length 1 is, as they go up and up and up, they get closer and closer and closer together. And so if we give them an equal share of the energy, we would imagine mathematically that most of the energy would come up in really, really short wavelength. There's an equal problem at the lower end. So if we say, okay, if we limit how much energy can go out, we have an equal problem at the lower end, that we don't see very much energy coming out at very low energy. So at the low end, in a classical system, if we imagine a wave on the sea, and we have a tidal, so not a tidal, if we have a wave energy power station, so we have a meter of shoreline, and we take all the energy from the wave that comes in, that's the sea wave. It doesn't matter what the wavelength of this wave is. If we wait long enough, we will get however much energy. So if we say we need a megajoule of energy, if we reduce the frequency of this wave so it has less energy, all it means is we have to wait longer to get that same amount of energy. So the longer we wait, the more energy we get. Obviously, the higher the frequency, the less time it takes to get the same energy. Or if we make it wider, we also get more energy in less time. So effectively, the power goes up by the length that we have, and water waves behave like that, but light waves don't. So if we take photoelectric effect, which is his example, it's also my favorite example, and it's the historical one. If we take a piece of metal and we apply a voltage, let's apply a voltage and have another piece of metal in a vacuum. If we shine a light on it, we can make electrons fly out, and they go onto our other electrode and a current flows. If we measure how that occurs with different colors of light, what we find, so if this is the energy of the light, what we find is nothing happens, and then there's a step, and then it carries on, and then there's another step eventually. Why is that? It's because there is discrete energy levels inside here that we're actually shooting the electrons out. We need a certain amount of energy to do that, and it doesn't matter that our red light, for example, can be brighter or darker. If we turn our red light up, nothing happens. It doesn't make electrons come out, so we cannot just wait longer with light. In my example, which is also on my YouTube site, if we take chlorine and hydrogen and we shine different colors of light on it, Nothing happens if the light is redder than a certain color of green. If it's too red, it doesn't have enough energy to break this bond. It's the chlorine-chlorine bond that breaks. But if it is bluer than that, it can do this reaction. It can break the chlorine-chlorine bond and cause an explosion. In my example, I shine a red and a yellow light on it and nothing happens, and I go straight to blue for practical reasons, because green sometimes just starts the reaction and uses it up and doesn't work very well. But from a physics point of view, it's interesting because we can shine a red light on there for a really long time and nothing happens. We can shine a really bright red light on there and nothing happens unless it's really, really incredibly bright. So what does that mean for us? It means that if we heat up a system with particles that have energy levels that they can go in that are discrete, so for example, the vibrational energy levels of a molecule, or for example, the electron energy levels inside a solid, we can take these and distribute them into this energy diagram. And the simple rule is, if we do it thermally, so if we heat it up, we cannot have more electrons in a higher level or more energy states in a higher level than we do in the layer below. So that means we have to generate some kind of triangle shape of energy states, no matter how hot we make it. Obviously, the angle of this triangle goes down as it gets hotter because we get more and more states that are activated. If we cool it down, it gets fatter and fatter and shorter and shorter. If we do it with light, we have a different effect that relates to our Frank Condon and Born-Oppenheimer approximation, because it's the same effective physics that's doing it, that when the light hits our electron typically, it will be excited and the rest of the molecule can't react in time. So in this case, the energy from the photon doesn't get distributed. It has to all go somewhere initially, then it can be distributed afterwards. So if we take the ground state of this, whatever it is, and we excite it optically with enough energy to go to the second level, we can excite them directly to the second level and not to the first level, and then they will have to fall back down thermally, so it will have to decay afterwards. But our initial case is not the same as the thermal case. We don't have any in this intermediate state. We jump straight over it into the second excited state in that case. So we have completely different effects that occur when we shine a light on things and when we heat it up. If we heat up the hydrogen and chlorine mixture, we have to get it quite hot before we get that activation, because there are a lot of vibrational energy levels in between. If we do it optically, we can make sure that every bit of energy goes into breaking that bond. So the last thing that I want to bring into this discussion is the problem of a laser effect. We have a new problem. Let's start from the ground state. If we start from the ground state, we excite to the ground state as well, which is, as we know, not very likely, but let's do it. We have a new problem that if we have a lot of states, a lot of molecules in this ground state, and we excite them up to here, the same photon that does the excitation will also shake this one back down and cause a stimulated emission. So what is a stimulated emission? We've got our light comes in and it promotes this ground state molecule into the excited state. So it gives its energy, pops it up to the higher energy state. But if it hits it when it's in its excited state, it knocks it back down again and we get the light back. That is a problem, because if we want to make a laser, we need a lot of molecules in this excited state, and we want them to all come down at the same time. When they emit photons of this wavelength, they should excite each other and generate a cascade and give out a lot of light. Equally, The problem is the same with sunglasses, for example. If my sunglasses absorb a certain color of light, and they're doing it by this kind of transition, and the problem is if I promote half of my molecules in my sunglasses up to the excited state, when they get hit by more light, none of it is absorbed. Some of it is absorbed, but some of it causes a new photon to come out, and on balance, in the sum, no photons can be absorbed. So we can get to a maximum, again we have a maximum, we can get a maximum of 50% in the excited state using this effect. And so if we look at that over time, we can see that when we start off with all of them in the ground state, our sunglasses are very black in that color, but when they get up to 50%, they're completely transparent in that color. All of the light intensity goes through. It's not the same light photons, but all of the intensity goes through. So weirdly, or catastrophically, if we try to use this effect to absorb a laser, for example, in laser goggles, it might be terrible, because if the laser is intense enough, it will excite all of the molecules to their excited state, and then, once half of them are in the excited state, it won't be very absorbent in that color at all. It will be slightly absorbent because they can fall down in other ways. They can lose the energy by hitting things. But if the light is intense enough, a lot of it is going to get through, and a lot more than did at the start. So laser goggles usually aren't, or are a big problem. If we use the wrong laser goggles, a lot of the laser light will get through. Typically, a laser would work much more like our phosphorescence worked, which is that the light excites a normal transition that we would expect, maybe to the second excited state, then it goes down by hitting things. Then it transfers into a different state. So in our phosphorescence model, this would be a different spin of the electron, which we're not allowed to do with our photon on its own. If it was a semiconductor, it would be a different atom. In a gas laser, typically, it would be a different gas molecule. So it excites, the energy is transferred into a different state, and in this case, we can gather our what's called a population inversion, where we've got more in the excited state than we have in the ground state, because we're exciting into this state here. So we're allowed to have half of them in the bottom here and half of them in here, but if they're fed out to here and captured, then we can carry on building this up. This can always be half. If we have this as a separate molecule or a separate excitation center, so if it's a ruby laser, for example, this is a different metal. If this is a separate excitation center, then the number of these are not the same. If it's the same molecule, then it's going up and it's being lost into this state, so we can gradually pump it into this state, and then either by chance or deliberately we can fire the laser by letting this decay, and it causes, once one is released, it causes an avalanche of all of these to be released. But this is a redder color, less energy than this one, because it must be, we can't generate energy unless we use a 2-photon transfer. So for the sake of completion, 2-photon transfer, the weakness of my argument with the red and the green and the whatever yellow light, if we have an incredibly intense beam, it is possible for 2 photons to hit our molecule or our electron at the same time, so very, very close together in time, and then, so let's put it as 2, let's put an arrow in between, then we can have twice the transition, a 2-photon excitation. But because of our Frank Condon, Born-Oppenheimer, whatever we want to call it, because of the assumption, because of the need that the energy goes straight into an actual energy state, And because it would otherwise drop down again very quickly, these two have to be very close to each other. Because molecules are very small and photons are also very small, that means we need a very, very intense light source to do this, and it's almost only possible with a laser. So we have a laser focused into a spot, and it can do this. This is a known effect, but practically it is very hard to do. So practically it would be hard to have a 2-photon transfer into the excited state just by having a normal light shining on it. It would have to be a very intense light to be able to get 2 photons in. But this is a very useful effect when we want it, because it takes 2 photons to get into there, so nothing is going to happen with stray light. It is only going to happen right in the center of our beam where we've got a huge intensity. But that is just an aside to explain why it is not 100% correct that red light cannot excite a higher energy transition. It sometimes happens, but only when it's really, really intense. Okay, I'll stop it there because I've given you 2 other videos to watch. The one on photoelectric effect and the one on Planck, which tells us why thermal energy gives us a Boltzmann distribution of energy. So the Boltzmann distribution is what we see if we look at a black body or sunlight, or if we look in the camera here and ask it what is it doing, it is assuming that the light, so this would be energy or this would be intensity, sorry, I, number of photons maybe, and this would be energy or wavelength, slightly different if we use different axes, and the shape is like this. That is because if we have a photon with no energy, that doesn't exist. So this must be 0. We can't have negative energy, so that is also got to be 0. And as we increase the amount of energy, we get more and more photons, and then it goes back down again. And that is a direct result of Boltzmann mechanics. Have a look at those 2 videos. Have a think about this. We'll come back with more spectroscopy later.